Okay, so I really hope you watched the Tuesday class, or at least have read chapter 3 and 6 pretty closely. All right, because I'm gonna launch into this stuff as if you were here on Tuesday. I'll definitely explain stuff along the way, but. All right, so okay, so I've written an acid and a base on the board. I'd like you to draw the products of this reaction. I'd like you to draw the mechanism for the reaction and a reaction energy diagram. And while you do that, I'm going to draw a pKa table on the board. Yeah.
When you say mechanism, is that just like draw the flow of electrons with arrows?
Curved arrows, yep. everybody should take a moment to recognize a historic event. It's the first time we've had 30 people in this room, so thanks for coming. So the next historic event will be somebody else showing up. That'll be the big one. I count in that. So yeah, if you came in late, basically just answer the 3 questions on the reaction over on the left board. I'll give you another 90 seconds or so. Okay, so if you think you're close, keep working on it. If you're just totally lost, you can watch what I do. So chapter 3, acid-base reactions, mechanism, reaction energy diagrams, discussion of transition states, rates, thermodynamics, all that stuff is in chapter 6. Acid-base chemistry proper is in chapter 3. And I sort of work them all in together. You're going to probably use 6 as a reference to come back to as we continue talking about reactions. So in an acid-base reaction, a Bronsted acid-base reaction, you have to figure out which proton is the most acidic, and you have to figure out which atom, or bond maybe, but which atom is the most basic. All right. Once you do that, because the reaction is always going to be between the strongest acid and the strongest base. All right. There may be other weaker acids and bases in there, and it could be that those weaker acids and bases also react. But the first reaction is always going to be between the strongest acid and the base, strongest base. All right, so here we've got, I went in and I drew H's sort of all over the place. There are a lot of H's. We have one hydrogen that's on an oxygen. All right, so the OH bond is the most polar bond in these molecules, and the oxygen is going to be the one that's most able to absorb extra electrons. All right, so generally, protons on carbons are not, I mean, it's organic chemistry, so certainly in organic 2, maybe a little bit in this class, you'll see protons on carbons act as acids. They're really weak acids. I'm going to talk more about this pKa table here in a minute, and you don't necessarily have to copy this all down right now, okay? You probably should write this down at some point. If you had some time there, that's fine, but it'll be on the video, right? But down here at the bottom, where the weak acids are, the really high pKa values, you start seeing H's bonded to carbon. All right, CH bonds are not terribly polar usually, and a carbon is not a very electronegative element, so it doesn't absorb that negative charge very well. So the weakest acid you're going to find, certainly in organic chemistry, is going to be just like an sp3CH, where that sp3 carbon's just bonded to other sp3 carbons. You get a full, if you pull the proton off, you get a full localized charge on carbon. All right, that's not a very stable situation. So as you look at this, right, you have no idea going in acid or base. Right? It doesn't have to be acid and base. You'll also note I don't put a plus sign there. All right. You do reactions. You're going to do your first reaction next week in lab. You pour chemicals into a flask or a test tube or a beaker, and stuff happens. Right? There's no plus necessary. Also, I think adding a plus to your reactions tends to confuse. You might think there's a charge there. So I like to just leave it off. So this is just two things mixed together. This could be the acid, that could be the base. This could be the base, that could be the acid. It doesn't have to be an acid-base reaction. There are a lot of different kinds of reactions. All right, so, but use, some strategy at the beginning. Right now, the only reaction you guys have seen in this class is an acid-base reaction. So the product here is probably going to be an acid-base product. So like I said, you've got one OH. If you pull a proton off of, if a molecule acts as an acid, it's going to lose a proton. Whatever that proton was bonded to is going to get the electrons that were in that bond. So it's going to gain electrons. Oxygen's going to gain electrons easier than any other atom. At the same, so that probably makes this the acid, the OH the acid. Same time, you've only got one atom in the two molecules that has an excess of electrons. So a base, in the Lewis definition, is an electron donor. All right? That applies in the Bronsted definition, it's a proton acceptor. Lewis acid-base definitions are more broad than the Bronsted definition. Bronsted focuses only on acids that are proton donors. But there are a lot of different kinds of acids. So a Lewis acid is an electron acceptor. A Lewis base is an electron donor. That Lewis definition works really well for even Bronsted reactions. To find the base, you're looking for the atom that will give away electrons the easiest. Okay, so if we look at this, O minus, right, the carbons don't have electrons, the H's don't have electrons, the C and the H's share electrons, and a bond can be an acid. That could be the source of the electrons, a bond. But sigma bonds aren't going to do that very well. That O minus is going to be the base. Okay, so if we look at this, you're going to have a base and an acid. All right, so once I've identified the acidic H and the basic atom, the product is simply moving the hydrogen from the acid, the H that you've identified as being the most acidic, move that H to the most basic atom. All right, so in this case, it would be moving this hydrogen to this oxygen. So if I draw that in, I'm going to leave out all these other hydrogens now. Yeah. All right, so that would be my products. I'd get a conjugate acid and a conjugate base. I said this in the last class. There's nothing magic about the word conjugate here. A conjugate acid's an acid. Conjugate base is a base. We're only sort of, it lets us talk about that. I can say conjugate acid, and you know I'm talking about the right side of the equation. Right? In solution, a molecule is either an acid or a base. It doesn't know that it's a conjugate. Okay, so that's the products. The mechanism is curved arrows. There was a question about this. An organic chemist refers to the series of curved arrows that show how the reaction takes place as a mechanism. Okay, so let me put that in here. You guys want to follow along while I do this, all right? So the curved arrows always start with electrons. Chemical reactions involve the breaking and formation of bonds. Bonds are electrons. So the way to keep track of what's going on in a reaction is always to follow the electrons. It's going to be really tempting to follow the atoms. Right? People, especially in this reaction, people are always wanting to draw an arrow from the H to where it goes. Right? So they would want to draw an arrow from here to there saying, this H moves there. I mean, that has a certain logic to it. And it would probably explain this reaction okay. But it doesn't explain most reactions. And you're still left with how to deal with electrons. So focus on the electrons. So here we've got excess electrons on the base. It's the electron donor. And so the arrow is going to start on that basic atom and go to this H. And literally what that arrow says is 2 electrons go from the oxygen to the proton and make a bond. Now, if that happens, that can't be the whole mechanism, because this arrow says this O makes a bond to that H. If that's the only arrow you put in there, that H has 2 bonds, and H can't have 2 bonds. Okay, so you need another arrow that says, H is going to give up the electrons it shares with this oxygen. So you have a lone pair on the basic atom that becomes a bonding pair to the H. Then you have a bonding OH pair that becomes a lone pair on an O. And the curved arrows can get really out of hand, all right? Remember, these molecules are real, tangible things in solution. So the base is not like throwing electrons like a lasso, okay? What actually has to happen is a lone pair on this oxygen has to collide with this hydrogen. All right, we have partial negative O, a partial positive H. So there's some electrostatic interaction there. That negative O is electrostatically attracted to the partial positive H. And literally, when these things hit, they hit in a linear fashion, okay? So the oxygen with the electrons, the basic oxygen, has to come from directly behind the hydrogen. So at the high energy point, where that bond is made and broken, the 3 atoms are linear. But that gets cumbersome to write. I don't want to have to always draw my molecules that way. So the curved arrow is just sort of saying, it's indicating the electrons go here, but the whole molecule has to follow the electrons. All right, that's a mechanism. So, any questions up to now? How I got the products, how I identified acids and bases, how I drew my mechanism. All right, so the reaction energy diagram is just energy versus a reaction coordinate. You guys will remember this from Newman projections. Right? We would plot energy versus dihedral angle as we rotate through a full bond rotation. So that coordinate on the x-axis is a real thing, but it can kind of be a lot of different things. Here, probably it's going to be, the OH bond distance would be the easiest thing to plot this as. And energy is really Gibbs free energy. All right, and that is, chapter 6, you could probably spend 4 or 5 PhDs studying chapter 6. All right, the thermodynamics of these reactions and the kinetics of these reactions is pretty involved. I put this up on the last one. I'll put it up again. The Gibbs free energy change in a reaction, or any process, actually. All right, so that Gibbs free energy change, and that's going to tell us whether the reaction is favored or not. All right? If the Gibbs free energy goes down, the reaction's favored. If it goes up, it's not favored. When I say it's not favored, I mean the way I've drawn it here, the left would be favored. All right? Everything exists in equilibrium. And so if you have 4 molecules that are all pretty close to the same energy, or reasonably close to the same energy, you're going to have a mixture of them at equilibrium. The Gibbs free energy is going to tell you how much of each you have. So this change in Gibbs free energy is equal to the change in enthalpy. For this class, basically that means bond energies. Delta H is all about bonds. If you break a weak bond and make a strong bond, your delta H goes down. Delta S is entropy. You probably think you know what entropy means. I'm not trying to insult you personally or the class individually, but if you don't do a pretty sophisticated mathematical analysis, you're not really getting to entropy. Entropy is not just the molecule or the molecules. It's the entire system. It's the solvent, it's byproducts, it's a whole host of things, all right? But what you know and what I'm going to kind of let stand is it's basically disorder. The more disordered the system, entropy goes down. And entropy always goes down. The universe in, I don't know how long, billions, trillions of years, will be pretty much a uniform sea of particles. Entropy will have gone as far down as it can go. So the universe is always trying to take entropy down. We measure in a chemical system, entropy is like the more molecules you have. So if you have a reaction where 1 molecule turns into 2, entropy goes way down. Even if enthalpy goes up, entropy goes way down for that. The other thing you can see here, and I'm not going to get into it too much, but delta G for a given system is temperature dependent. Right? So sometimes the equilibrium changes depending on if the reaction's higher temperature or lower temperature. And this all ties, delta G is also equal to this. All right, so delta G is equal to the negative value of the gas constant times the temperature times the natural logarithm of the equilibrium constant. I'm not going to ask you guys to solve an equation. All right? You guys are not going to have to solve. I don't know what the gas constant is. It's like 8 something in some unit. All right, I know more than that. But this is not going to be a quantitative class. In Chem 280, you'll probably do a fair bit with this. What I want you to be able to do is sort of estimate which side of the equation is favored. All right, so before I draw a curve on this diagram, if you drew a reaction energy diagram, you should have done this. If you didn't do it quite right. Which side, left or right, that is, which pair of molecules is most stable? Think about it for 30 seconds, or you can just answer me. Everybody else think about it for 30 seconds. She said she knows what it is.
It's the right side.
And then you told everybody. Don't play poker. Don't play poker.
Yeah, no, I said
All right, we have a vote for the right. Anybody disagree with that? Why? Why is it the right?
Because if you compare the bases on each side, what did we do? Oh, like you want to see which one the negative charge is more spread out across the atom.
Yeah. So this came up I put this up, and I didn't really do much with it. The book has this ARIO method of figuring out which side is favored. That usually is looking at the base. Doesn't have to be the base. You can apply it also to the acid, but it's usually easier to do this with the base. ARIO stands for atom, resonance, induction, and orbital. In this case, we're on induction. Okay, so the atom, to use this method, you sort of would look at either the charge or the excess electrons. Again, the base is going to be an electron donor, so there's like these excess electrons somewhere. In this reaction, it's illustrated by a negative charge. Okay, so look at that negative charge. Now, what atom is the negative charge on? Well, on the base on the left, we're going to compare that with the base on the right. So you're always comparing, anytime you want to judge stability or which side is favored in an acid-base reaction, you either compare the two acids or you compare the two bases. You can't compare an acid and a base. You really can't compare like the base and its conjugate acid. I mean, they're, like obviously ethanol is more stable than its conjugate base. But that didn't tell you anything. You need to know about both partners. So either compare the two bases or compare the two acids. Generally, the way to compare the two acids is with a pKa value, and we'll get to that in a second. For the base, in this case, the negative charge, you're looking at which of those negative charges is more stable. So A says, look at the atom the negative charge is on. All else being equal, if you have the negative charge on a more electronegative element, that's more stable. Right? So an O versus an N, or O versus a C. The O would be favored. But here, that doesn't help, right? O, O. So the negative charge is on oxygen on both sides. Then you look at resonance. Is the charge delocalized? Is that charge spread out by resonance? Nope. Right? The atom next to the O minus is sp3. That carbon already has 4 bonds. Can't make 5 bonds. It can't donate. It can't accept electrons. It can't give electrons. That sp3 atom is for resonance is dead. So we would say this oxygen has a localized negative charge. When I say localized, I mean the negative charge is completely and only on that oxygen. If there were a resonance, if I could draw a resonance structure with that O minus, if I could take that minus and I could push it and make a bond somewhere else, then it would be delocalized. And delocalized charges tend to be more stable. Same thing over here on the right, localized O minus. So A and R are a wash. The orbital, actually, I'm going to skip I. Don't skip I. You're not allowed to skip letters here, but that O is sp3. The O over there is sp3. The excess electrons are in an sp3 orbital either way, so that's a wash. But induction is another thing. Induction is sort of like resonance, but without an actual resonance structure. And so what you have to look at here is, right, the carbon-fluorine bond. Fluorine is the most electronegative element. So if you have a fluorine on a carbon, that bond is strongly polarized, just like a carbon-oxygen bond is strongly polarized. The fluorine's pulling electron density toward it. That makes this carbon partial positive. Well, if you pull electron density away from the carbon, that carbon's going to want more electrons, right? I use money probably too much as analogies here, but if someone takes 20 bucks from me, in addition to being angry and wanting revenge and all that stuff, like the other thing I want is 20 bucks. Like I would like more money. I would like to buy lunch, and I don't have $20 now, right? So if the fluorine takes electrons away from that carbon, the carbon's going to want, the carbon itself, a carbon bonded to fluorine is actually more electronegative than a carbon bonded to H. And so this sort of propagates through. This is a really strong dipole. That makes this kind of a weaker dipole. And then you get a dipole sort of like that. So an inductive effect is through sigma bonds. So basically R here is through pi bonds. I is through sigma bonds. And that makes I a lot weaker. The inductive effects tend to be quite a bit weaker than resonance effect. But if that's all there is, if there is no resonance effect, that's going to be the bigger effect. So by putting these 3 fluorines on the carbon, I didn't mention that, right? There's 3 fluorines there. If there was only 1, the inductive effect would be less. But there's 3, so it's more. Congratulations. 3 is greater than 1. All right, so that inductive effect helps stabilize that O minus just a little bit. So yeah, the right side is favored, and you can indicate this a whole bunch of different ways. You can draw me an arrow like that. You could draw an arrow where like the one going to the right's a little bigger than the one going left. You could write favored over that. You guys have words. You can tell me which side's favored. So once you've done that, though, now you can draw this energy diagram. All right, the way this works, the lower the delta G is, the more favored it is. Okay, so the lower side here is going to be favored. If the right is favored, you want the right side of this curve to be lower. If the left were favored, you'd want it to be lower. Okay, and then there's a couple of other things in this diagram. So reactants, product. Delta G is here. All right, that's thermodynamics. The difference in stability between the reactants and the products is not something you can change. Right? How stable something is just what it is. You may have seen this somewhere. The energy of activation is basically how much energy do these molecules have to get over the hump. And again, this is kinetics. So down at the bottom, all right, down at the bottom where delta G is, we call that thermodynamics. You're looking at the equilibrium constant, you're looking at stability, and you really can't affect that, all right? That's just what it is. The area up here above with energy of activation, this is kinetics. By the way, I abbreviate reaction RXN an awful lot. I usually wait until like the last week of Orgo 1 to tell anybody that. Most people figure it out, but that's what I'm saying by RXN. All right, so above this line, above the energy of the reactant, or above the energy of the highest energy part, this tells you how fast the reaction's going. So a faster reaction has a lower energy of activation. A really slow reaction has a higher energy. And a lot goes into that. Okay, again, you can make a career out of studying all the factors that go into the energy of activation. But some of it is like physically how accessible. Like if you look at what's going on in this reaction, this oxygen has to collide with that hydrogen in a linear fashion. Right? So OHO. How difficult is that to achieve? Right? If you imagine, right, if I put a whole bunch of bulky stuff around the basic atom, that's going to be a little slower. If I put a whole bunch of bulky stuff around the OH, it'll be slower. As it turns out, acid-base proton transfer reactions tend to happen really fast. Protons, by definition, because they're not bonded to anything else, have to be on the outside of the molecule. Okay, so it's possible to sort of bulk up the base, but it's a little harder to bulk up the acid. We're about to see, the next things we're going to look at are chemical reactions that aren't proton transfers, right? So, you know, a carbon attacking or being attacked by a sulfur that's bonded to other stuff, making a carbon-sulfur bond, for instance. All right, now you can sort of have physical barriers to that happening. The other thing is, you know, how likely is it we can achieve this geometry where they're linear? Is there something that just completely prohibits that from happening? If there is, the reaction won't happen. No matter how favorable it might be, if the basic atom, the H, and the atom that the H is bonded to can't form a line, reaction doesn't happen. Again, that's pretty rare, but it's something you should have to consider. Energy of activation also changes with temperature, and the reason for that is these molecules have to physically collide. So again, the mechanism is a nice way of thinking about the electrons, but it's not an accurate representation of what happens with the molecules. The molecules are physically colliding. Right? So if I increase the temperature, the molecules move more. They bang into things more often. Right? It's why it's hard to do a reaction in solid. It's why we usually use a solvent. Again, you guys haven't done a reaction in lab yet, but usually when you do a reaction, there's a solvent, a liquid medium where the molecules can move around in. If you have your two reagents in the gas phase, right, they're very non-dense, collisions are more rare, the reaction slows down. If you have your reagents in the solid phase, molecules aren't moving any. Right, they're just sitting there, so that goes slow. So liquid phase reactions tend to be, in organic chemistry, liquid phase reactions are the most common. All right, so like I said, if you wanted to represent here a slower reaction, you would raise this. If you wanted to represent a more favorable reaction, you would increase the gap here. And you always, really for this, the main thing that I'm asking you to do is show me which side's favored. The side you think is favored should be lower on the diagram. Questions about that? All right, you know everything then. Good. Okay, so I wanted to show this pKa table. I wanted to actually draw it. Like I said, you should physically write. Yeah, sorry.
I have a quick question about the arrows. Like when we're done with the column, does it matter if we change the arrows with like one shorter, one longer? Does that make a difference?
Like these?
Yeah.
So like if you look at questions on these, I'll typically ask which side's favored at equilibrium. You can use the long arrow over a short arrow. You can just draw one arrow. You can say this side's favored. I know a lot of times paranoid students on an exam will do like all of them. Circle it, daggers, like this is what the side. Yeah, so I don't really care. Like, I mean, what I want is you guys to tell me which side you think is favored. And so, yeah, I mean, I wouldn't leave it super. If you're going to use one arrow, and I'm not trying to make anybody paranoid. I think this is pretty clear that the top one's longer than the bottom one. I have, and also, like I did this too as a student. I'm not laughing at any individual in particular, just sort of all of us when we take exams. Right? I've had people try to draw them both pretty close and then come and argue later, like, no, I meant, like that bottom arrow is longer, right? And yeah, I won't go, like if you're gonna use that, it's gotta be really clear. I think it's easiest just to write favored on the side you think that's favored. Yeah.
You say favored, is that just the formation of more of those molecules?
Yeah, so that's a good question. At equilibrium, when I say this side is favored, there's something else I need to come back to. That I missed my segue to the pKa table. Thanks. So when I say this side is favored, I mean at equilibrium, there's more of the molecules on the right than there would be on the left. In this particular case, at equilibrium, it's not going to be 0 on the left. Really, not a whole lot of reactions are completely irreversible. And biochemically, this is really true. Right? I think, and again, I'm not trying to discriminate against non-pre-med folks in the room. I was a non-pre-med folks. Oh, that's going to be good at home. But if you're pre-med, where you're going with all this is chemistry that takes place in water. So water's your solvent. All right, so most biochemically interesting reactions are not irreversible. Enzymes can sort of catalyze them going either way. And for a lot of them, like the reaction goes one way under one metabolic condition and it goes the other way at other times, right? I'm getting way off the topic. I didn't turn it off. That's good. All right. So, yeah, at equilibrium, there'll be more molecules on the right than there are on the left. Let's look at pKa. Let me see where I can write this. pKa is a physical characteristic. It's a constant for a molecule. So ethanol has a pKa of 16. No, sorry, that's not ethanol. Trifluoroethanol has a pKa of 12. Ethanol has a pKa of 16. All right. pKa's above 14, pKa's below 0 really don't exist. All right. The strongest acid you can have in water is H3O+. Any acid that's a stronger acid than H3O+, will just protonate water and make H3O+. Same token, the strongest base you can have in water is hydroxide. Any base that's stronger than hydroxide will just deprotonate water and you'll get hydroxide. All right? So there's a leveling effect. In organic chemistry, though, we often do reactions that are not in water. That's what makes us special. That's why it's its own course. All right, so if your reaction's not running in water, you can have bases way stronger than hydroxide. You can have acids way stronger than H3O+. Like trifluoroethanol is not really a strong enough. Trifluoromethoxide is not a strong enough base, but ethoxide, you can't really have ethoxide in water. Right? It's just going to pull a proton off water and you get hydroxide. But there's some things that come out of this. So the equilibrium constant, this falls out of the Henderson-Hasselbalch equation. So can he do this? All right, so the equilibrium constant, and again, this is pretty approximate, but it's organic chemistry, so all the math is approximate. You can do really quantitative physical organic chemistry. It's an important subfield, but for this class, I'm just trying to illustrate concepts. So the equilibrium constant here is going to be 10 raised to the power of the pKa of the favored side minus the pKa of the unfavored side. All right, this is going to be 10 to the 16 minus 12, or 10 to the 4. So the equilibrium constant here is 10,000. Keeps coming up 10,000. I think it's exactly the thing I had in last class. 10,000 is a big number, right? But if you've got 10 to the 23rd molecules, 10,000 is not very much. Okay, so at equilibrium, for every pair I have of these two, I've got 10,000 of these. But if I multiply both of those by like 10 to the 23rd, I have a lot of both of them. All right, and the other thing is a real important concept about equilibrium. Equilibrium kind of implies stasis, right? That everything has just frozen. That's not what happens. So at equilibrium, you're going to have 10,000 of these, one of those, but the molecules themselves will go back and forth. Both reactions, the forward and the back reaction, will keep happening. It works out that the forward reaction, in this case, the rate of the forward reaction is 10,000 times that of the back reaction. Okay, so if I could just follow a single proton, okay, I'm not looking at the whole population, I'm just on a proton. All right, I put a little GoPro on this proton. I will find that that proton spends 10,000 seconds on ethanol, just ethanol by itself, and it spends 1 second on trifluoroethanol. Like it's going to constantly bounce back and forth. Right? And the bigger the equilibrium constant, so if the equilibrium constant were 1 billion, there'd be 1 billion of these, 1 of these. Rate of the forward reaction is 1 billion times the back reaction. Okay? There's another cool thing that comes out of Henderson-Hasselbalch. Let's just look at, and this is properly with water. So if you have, I'm just going to draw a generic base here. Okay? So we're just looking at HA here. If the pKa, I guess this would be water. Let's call this water. The base is going to be water because pKa is properly made it like 45 minutes without terrible catastrophe? All right, so if the pKa equals the pH, then the concentration of the protonated form of the acid is equal to the deprotonated form. Okay, so if you look over here, acetic acid has a pKa of 4.5. So at pH 4.5, if I put acetic acid in pH 4.5 buffer, I will have 50% acetic acid and 50% acetate. Acetate's the deprotonated form of acetic acid. All right. If the pH is less than the pKa, remember as pH goes down, the solution's more acidic, got more protons. So under more acidic conditions, the concentration of the protonated form will be greater than the deprotonated form. Right? As we have an abundance of protons, we're going to protonate A. We'll go back to HA. And then going the other way, if the solution is more basic than the pKa, so if the pH is greater than the pKa, then the concentration of the deprotonated form is greater than the protonated form. So at pH 7, right, a carboxylic acid, say acetic acid, our blood is about pH 7.4. Some of you may be 7.39, I might be 7.42, others are 7.41. Nobody's outside of that range, really. I know that because we're all conscious, mostly. I know, 50 minutes into an orgo class, maybe some of you are at 7.44. All right, so that was a good, you'll like that once you take biochemistry. That was a good joke. So anyway, this is just sort of a way to keep tabs on, is the protonated form of the acid more abundant than the deprotonated form, or vice versa, or unusually, right? Statistically, this one's not going to happen very often. So you look at acetic acid, pH of 4.5, pKa of 4.5. My blood is pH 7.4. 7.4 is more basic than 4.5. And so if I shoot some acetic acid in my blood, bad idea. There's already some there. I don't have to shoot it in there, but right? It's going to be mostly acetate. It's going to be mostly the deprotonated form. So carboxylic acids, so again, hopefully you saw Tuesday's class. I put up there a reaction between a carboxylic acid and an amine, sort of biochemistry's strong acid and strong base. That always favors, the amine is always going to deprotonate the carboxylic acid. At physiological pH, carboxylic acids are always going to be mostly deprotonated by about 3 or 4 orders of magnitude, right? 1,000, 10,000 fold. Going the same way, amines are going to have a pKa of about 10 to 11, all right? So pH 7.4 is more acidic than their pKa. So an amine under physiological conditions is almost always going to be protonated, again, by 3 or 4 orders of magnitude. And 3 or 4 orders of magnitude, I keep saying this, sounds like a lot, right? If I could increase my wealth by 3 orders of magnitude, I probably wouldn't show up Tuesday. No, I'm more dedicated than that. I would finish the semester. All right. So 3 orders of magnitude is a lot. But again, you've got oodles of molecules. Having a 3 or 4 order magnitude difference means while the protonated form may be the dominant one, if the chemistry required to do something requires the deprotonated form, it's there and can happen. Okay, so this brings us to the pKa table. And like I said, I would like you guys to write this down at some point. Doesn't have to be in this class right now if you want to watch me talk about it. I'm gonna kind of go through here and break it out a little bit. The first thing I want to point out is I've put the strong acids higher up. So we've got the acid, the pKa of the acid, and then the conjugate base of the acid. And some of these molecules will show up more than once, right? Here's water, and there's water. Water is one of those molecules that can be a base and an acid. So water is the conjugate base of H3O+. It's an acid that has a conjugate base of hydroxide. Okay, so, and the other thing I would say is you really don't need to memorize any numbers on this table. You need to have the order under your belt, and you need to have like ballpark numbers. Nobody ever likes it when I say that. All right, so we've kind of got what we would call strong acids. And there are, this is not an exhaustive list of acids by any stretch of the imagination. But sulfuric acid in organic chemistry is really going to be the strongest acid you're going to see. pKa is -10. And like I said, any pKa that's lower than 0 or higher than 14 is at best an estimate. pKa, by definition, is in water. Right? And I can't have an acid that's got a pKa of -5 in water. I'm just going to wind up with H3O+. Okay, and then carboxylic acids. So really, depending on what the R is here, right? Acetic acid is 4.5. Depending on what that R group is, this might be pKa's, 3 to 5. There's even, so trifluoroacetic acid, same definition over there, or the same thing over here. The pKa, I think, is 1.7. Might even be stronger than that. Right? By putting those 3 fluorines on there, you make the carboxylic acid even more acidic. So you just want to kind of have, low single digits for carboxylic acids in mind. Trimethylammonium has a pKa of 9.8. So if I pull this H off, the conjugate base of trimethylammonium is trimethylamine. So again, here we're just going to look at nitrogens, quaternary nitrogens that have a proton on them are going to be kind of 9 to 11. All right, now a lot of people are writing, which is good. I always hated that as a student. Like professors, teachers tend to spend half their time telling you to take better notes and half their time telling you to stop writing and look what I'm doing. So the thing I want to draw your attention to is the pKa of NHs. So down here, really low, ammonia you know as a base. Ammonia is a pretty good base. Ammonia is the conjugate base of NH4+. NH4+ is in this ballpark. NH4+ has a pKa of about 9.2. And its conjugate base is NH3. And so NH3 is just like water, right? NH4+ is like H3O+. Fairly strong acid, 9.2. Ammonia is the conjugate base of ammonium. But ammonia is also acidic. You can pull one of those H's off of a neutral nitrogen and get NH2-. That's like hydroxide. Just all the numbers are different. So NH2-, the conjugate base of ammonia, the pKa to do that one is 32. I'm always seeing students confusing NH4 to NH3 pKa for NH3 to NH2. Right? NH4+ is a mild acid. NH3 is a really weak acid. Anyway, you can sort of, the other one here, alcohols, like ethanol has a pKa of 16, methanol is like 15.8, T-butanol is 18. Like alcohols tend to come in 16 to 18. You guys can work the rest of this out. Here's the big thing. Strong acids are at the top. Weak acids are at the bottom. On the other side, on the base side, weak bases are at the top. Strong acids are at the bottom. So here is an important Okay, so the conjugate base of a strong acid is a weak base. The conjugate acid of a weak base, conjugate base of a weak acid is strong. The take home there is the strength of an acid and its conjugate base, or a base and its conjugate acid, are inversely related. A strong acid is going to have a weak conjugate base. Strong base is going to have a weak conjugate acid. Stuff in the middle is kind of moderate. The other thing is, any acid can protonate the base, and any of these acids can protonate a base below it. All right? Sulfuric acid can protonate all of these bases, even chloride. You can make dry HCl. So usually we encounter HCl in water. And in water, HCl is not really HCl. It's H3O plus and chloride. Because HCl is a strong enough acid to protonate water. But if I take table salt and I drop sulfuric acid onto it, the sulfuric acid protonates the chloride. HCl without water around it is a gas, so it volatilizes. And if you blow a stream of nitrogen or something dry through there, you can collect dry meaning no water HCl. You can also really, because now you can't see where the acid is, you can really burn yourself pretty good. All right, so acids high on the table can protonate the bases low on the table. Any base below it. Any base low can deprotonate an acid high. All right, so that's the way you use a pKa table. When you get a question like this, I might give you the pKa's. If I do, use it. This whole ARIO thing, all right, this is very general. Come on. All right, ARI is not a foolproof method. Even if you really, it's not even an expert-proof method, right? You can analyze it and just take a wrong turn with it. pKa is not. pKa is a measured thing. So if I tell you the pKa of this acid is 12.8 and this one's 10.1, the 12.8 one's favored. The side with the 12.8 is favored. The other thing you'll notice on these, so we used ARIO in this case to determine that the base on the right is more stable than the base on the left. That also means that the acid on the right is more stable than the acid on the left. Okay? The weaker acid, that is the more stable acid, and the weaker base, that is the more stable base, will always be on the same side. It took me a long time I don't know why it took me a long time to get that. When I say it, if you actually work through it, it makes sense, because you've got two things basically working in tandem. But if you're like me, you probably just need to memorize it. All right? The weaker acid and weaker base are on the same side. And that's why you don't have to do I don't have to analyze the acids. If I know that this base, if I conclude this base is more stable than the base on the other side, the right's favored. If I get pKa's and I know the pKa on the right is higher than the pKa on the left, I know the right is favored and I'm done. Right? I don't have to think about the base. Questions up to here? All right. what are the products and which side is favored? All right, so this one's, I ramped it up a little. I went slower through all that than I thought I would. So there's like 2 more examples that I had in there to lead up to this. Decided just to jump ahead. So one of these molecules has the word acid in its name. Again, it's acetic acid. That's not, I said this last time, and you'll see in organic 2, you'll see cases. Well, for example, if you mix acetic acid and sulfuric acid, you actually get a proton transfer like this. All right? So sulfuric acid is a really strong acid. So it can protonate the acetic acid. Even though acetic acid is an acid, right? You've got electron density on both of these oxygens, so they can act as bases. All right, so acetic acid in the reaction I asked you about could be a base if the other molecule is a really strong acid. I'm going to tell you that it's not. Okay, so if you said that acetic acid is going to act as an acid, congratulations. And if it is, right, acetic acid has protons on the carbon, it's got protons on the oxygen. The proton on the oxygen is going to be more acidic than the protons on the carbon. So again, the OH is a more acidic H than the NHs or the CHs or the NH. So that OH, this thing right here, is going to be our acid. So what's going to be the base? What atom is going to be the base? Got to vote for NH2. Anybody who thinks the NH2? Who doesn't think the NH2? All right, if you don't think the NH2, Which atom do you think? Got to vote for NH. Anybody else think NH? You voted twice, didn't you? Oh, okay. We're going to have an investigation on that, I think. Sorry. Try to keep that stuff out of here. Okay, so NH or NH2? Anybody think the C? Either of the C's? Good. So at this point, if you said the nitrogen, good. That we're okay on that. The question's going to be, and so both of them have electrons that could work as a base, right? So let's do both of these. And honestly, this is kind of the way you have to work it out. Well, actually, first of all, let me also do this. Let me, I did have kind of a, unreal. I had kind of an idea to illustrate this. Like if you really have just no idea, you basically have to try all the permutations. So let's use this oxygen, right, to take an NH. And if I do that, I get this. All right, probably nobody drew this. I kind of hope nobody drew this. But by drawing that, what I'm basically saying is I've got a neutral molecule, and I get two charged molecules. That better have bought me something. Delocalization of charge, something. I wind up with a protonated oxygen. But this charge, that positive charge is actually delocalized. Right? You'll notice I protonated the carbonyl over here as well. And this negative is delocalized. And again, you might think, well, that's all right. But we've basically moved a delocalized lone pair, sorry, a localized lone pair. We've taken electron density from an O and we've put it on N. Even delocalizing is not going to be enough for that. This board is ashamed and wants to disappear. All right, so we're going to actually get over here a strong acid and a strong base. You're never going to get, just again, as a general rule, if you look at what you've drawn in a reaction, you're never going to have a reaction that makes a strong acid and base together. Strong acids and bases together are going to react. All right, so then let's protonate this NH. We're all agreed that the OH is the more acidic atom, the most acidic H. So we're going to get acetate either way. So if we protonate the NH2, we get an NH3+. Purple arrow for protonating the NH. So draw them both out. Like at this point, honestly, we've got some people voting NH2, we've got some people voting NH. My guess is nobody's super confident about either of those. So draw them both out. You don't have to consider acetate at all. We're all agreed acetate is going to be the product. So trying to figure out which nitrogen gets the proton, the acetic acid, what happens to it doesn't matter because the same thing happens to it either way. So what I want you to do is compare these two. Compare the stability of those two molecules. Take like a minute and think about it. For one of those, you can draw a resonance structure. One of those two circles, one of those two structures I've circled, you can draw a resonance structure. Okay, so the structure you can draw a resonance structure for is the purple one. And it's got a lone pair here. I can move the lone pair from this nitrogen, make a pi bond, pi electrons, to put a lone pair, basically neutralize that positive charge on N. This is kind of the reverse of the acetate. Okay, on that carboxylate on the right that I put an X through, the O minus delocalizes over both O's. For this nitrogen arrangement, this lone pair still delocalizes over, or you could say the positive charge is delocalized. For the NH3, right, this nitrogen now has 4 single bonds. Okay, so that nitrogen has 4 single bonds. There's no pi bonds, there's no electrons, there's no way to move. I can't neutralize that charge. I think a lot of times people will be like, oh, just move these electrons down, right? And that would neutralize, I would give electrons to the nitrogen. The nitrogen would also suddenly have 10 electrons. Can't do that. This is as good a place as any to put this in. As you guys, I'm not saying, those of you that said NH2 got protonated, I'm not saying this is what you did. But as you keep thinking about resonance structures, as you think about structures, don't forget what we did in chapters 1 and 2, how many bonds things can have. There's a lot of times over here on something like this, if I don't draw these H's in, I'll just think, oh, minus can just go there, because I forget there's 2 H's already there. So the answer is this one. All right, so this reaction is going to give us that. Now, which side's favored? Products or starting material? Why? So this is the same, yeah, so the positive charge, again, everybody wants to say charges, and sometimes you're going to be right. This is where there's not like an ironclad rule. Charges, I think a lot of people at this point just think charges are bad. Charges are sometimes bad. Charges, all else being equal, are bad. But really what you've done here, we now have a delocalized positive and a delocalized negative. And if you just think about it, if you focus on it as charge, that sounds bad. If you focus on it as electrons, it sounds good. The electrons are delocalized in both molecules. The other way to think about it, so I'm saying you're wrong. The products are favored. The other way to think about it is, if I just had like ammonia here, if I just had an amine, we did that reaction last time. Hold on to that. An amine plus a carboxylic acid always favors the products. That's going to be an ammonium cation and a carboxylate anion. Even though you've got charges, those are favored. And that's with a localized positive on N. Here you've got a delocalized positive on N. So delocalized is better. All right, last thing I'm going to say, anytime you have a base that looks like this, that is a carbon something double bond with a lone pair, so oxygen O, N, S, something like that, and that carbon X double bond is bonded to something else with a lone pair, the proton will always go here. All right, the double bonded atom is going to be the one that gets protonated. And you go through the same sort of argument, like if you're feeling a little lost at that one, or the whole thing, I want to come back to fundamentals to wrap the class up. Identify the strongest acid, the proton that is the strongest acid. Identify the most basic atom, that is the atom that's going to give away electrons the best. To do that, you may need to draw the products of them and figure out, like, is charge delocalized? Is the product stable? Like, all of a sudden, this one over here has lots of different permutations. and I kind of flew through them. Hopefully you get to where you can identify that pretty quickly. If you keep in mind this periodic table, class is over, man. If you keep in mind this pKa table, again, ballparks. Alcohols are less acidic than carboxylic acids. They're more acidic than NHs, et cetera. If you keep that in mind, you'll be all right. That's it. Next week, well, you'll get an announcement. Read the email announcement about what we're doing next. And I have an office hour, I think starts at 2:30. I may be a hair late to it. I'll either be in my office or at the front of the building or on Zoom.